Everyone, welcome to this session. And Brandon from Manta Network will be speaking first. We're just getting his screen set up so that we can see him. So we'll start shortly.
Can you see it? Can you see it? Can you see anything? Brandon is on it, but he can't.
Amazing. Yes, we see you, Brandon, and we see your screen now. Thank you very much. And thank you to the audience for all your patience here.
Can everyone hear me? This is first time using this stuff here. Let's see. Yeah, hi everyone. Thanks for coming. This is super exciting to have this conference, and thanks to the organizers for putting this all together. Yeah, so I'm going to talk to you about OpenZL today, just the big picture, what we're building here. My name is Brandon Gomes. I work for Manta Network. We're building privacy infrastructure. And OpenZL is a new framework we built at Manta to speed up development of our private payment protocol, Manta Pay, our first one. And we thought it was so useful that we just open sourced it, make it a new public good for anyone building zk applications. And it's the new sort of middleware for the zk application stack. So let's get started. So over the past few years, there's been a huge explosion in the zk application tooling space, mostly accelerated by innovations on proof system side and programming language side that we use to build zk applications. The issue is with this increase, we've created a fragmented open source community, and every time we build new components, they're sort of isolated from each other and the ones that came before it. So after looking around this space, we found sort of three major problems that are created by this fragmentation. First problem is a lack of interoperability for common circuits. Most frameworks duplicate a lot of the work when building proof systems or gadget libraries and aren't able to leverage each other's existing work. The second problem is a large gap between proof system designers and programming language designers. Some of the coolest innovation in this space has come from the new proof systems that accelerate zk applications, but these new proof systems usually start out as academic prototypes, and then as engineers come in to optimize them, they stay in these niche code bases, take a very long time to sort of bubble up to app developers that are building actual products and to integrate with the tools that they're already used to using when deploying production code today. So this sort of long distance here is what doesn't allow us to sort of propel forward with the innovations that are coming out. And the third problem is, of course, the ever-increasing security surface. So as more and more code gets written, we have more and more code to audit to make sure that our systems are safe. Especially with these more and more complex systems coming out, the audits are getting harder and harder. And so we need to try and reduce the kind of volume of code that we're writing so that we don't have this growth of auditing surface. So to start tackling these problems, we built a new open source middleware solution called OpenZL. So what is OpenZL? What does it look like? So it's a framework for building zk applications that's built to leverage all the different open source tools that are already out there. It's centered around a new circuit description language called ECLAIR that lets us write zk circuits in a proof system agnostic way without sacrificing performance by enabling proof system specific optimizations across all circuits. So to compile ECLAIR into different proof systems, OpenZL is built on a modular architecture of plugins to support proof systems not just like GROS16, but also plonks and starks and whatever new thing comes out. And these plugins let you leverage the new proof system technologies into the ECLAIR programming language. But not just about proof systems, we also can integrate with custom front-end language support. So for languages like Lurk, which we'll hear about later today, and Noir and zkApps and whatever other languages people are using, we want to be able to integrate all this, the entire system together. And thirdly, the security plugins. So making sure that code auditing solutions like those developed at Veritice can be sort of directly injected into your development pipeline and support the circuits you're already building, independent of whether you're using different proof systems or different languages. So ECLAIR sort of tries to fit right in the middle there and allow us to bring together all the different parts of the ecosystem. So compared to high-level languages like Lurk and zkApps and Noir, ECLAIR gives us more direct control over proof system-specific optimizations at the cost of a more verbose encoding of circuits. So there's a trade-off here. But compared to proof system frameworks like ArcWorks, they give us a uniform way to express our circuits and give us a much better deployment pipeline for circuits as well, independent of what proof system we choose to use. If you look at any of these libraries, the way they're built, they sort of try to reinvent the wheel every time on how you deploy circuits, how do you build the verifiers on chain, how do you expose your proving and verifying keys. All this kind of stuff is done in a totally different way everywhere. And so we want to try and make that uniform so that developers sort of have the same experience across all proof systems. So how does ECLAIR OpenZL do this? Like, how is this even possible? So the most important piece of this puzzle is ECLAIR itself. So it's a new IR developed for OpenZL. It stands for Embedded Circuit Language and Intermediate Representation. And what it is a DSL embedded in Rust that lets us write circuits in a proof system agnostic way, but at the same time retain all the best performance characteristics of different proof systems. So the way we do this is we basically split the definition of a circuit into three different parts. The most important part is the gadget itself, which is the code that we use to describe the high-level constraints. Then there's the environment that the gadget lives in, and then on top, the compiler that can interpret the gadget in its environment. Here are the arrows on the right describe the dependency structure for these three components. So as you can see, a gadget can only make sense in an environment, and an environment only makes sense relative to a compiler. I'll go through an example in a bit here. The way we can think of this is we can think of the compiler as an execution engine for the gadget. If we use Rust as our compiler, that means we're just running the gadget natively on the CPU. So like you just write some code, it just runs on the CPU, executes, returns the output value. But instead, we can run the same exact code over a proof system plugin, and instead of just getting the value out, we get the witness generation and the proof of correctness, the zero-knowledge proof. So ECLAIR is extremely powerful, and that enables developers to sort of separate the high-level logic, what do you mean by your program, versus the low-level optimizations and the pipelining that you need to execute it in different environments. So to give an example, let's look at the Poseidon hash function and consider the environment and gadget that you need to build for it. So on the left, you can see the environment for Poseidon. It has three functions. It has the add round constants, the MDS matrix multiply, and the SBox operation. These functions define what I would call the instruction set architecture for the Poseidon gadget. Once we have these three primitives, we can define the hash function gadget as a composition of multiple rounds of calling these three functions. By separating out the environment, we give plugins like ArcWorks and its Gros16 prover and Plonky2 and Halo2 and whatever, the opportunity to optimize these primitive functions in the way that best suits their proving systems. So for R1CS, for example, where linear combinations are really cheap, or in Plonk, where we have custom gates, there may be a better way of writing SBox or add round constants in each proof system. And so we can do all of this without having to change the original gadget. So once we define the instruction set, we know what Poseidon hash function means, and then each proof system can decide how to best do the SBox, how to best do the add round constants, etc. So the benefit of this architecture is that it separates very cleanly the application from the optimization. And so people building proof systems who intimately understand how to optimize certain patterns in their proof systems can expose those optimizations to users. Whereas application developers, they don't have to think about it. They can just write their app. So later today, Todd will also give some more detailed explanation how this works for Poseidon specifically and how we've used it for private payment at Manta. So main idea here is that gadgets really live in an environment governed by the language features available to them. So if you think, for example, in a high-level language like zircon, you can think of the environment as like all operations you have available in R1CS. So think like addition and multiplication. Systems like PLONK, though, we have a lot more customizability in terms of what we call the smallest units of computation. Typically, these are called custom gates, and things like Plonky2 and Halo2 have these as language features. So what ECLAIR does is it makes this kind of language feature construction explicit through Rust traits, and it allows the developer to specify the instruction set for their gadget to best optimize its performance. And OpenZL itself comes bundled with a basic set of language features and pre-built gadgets. So the things you should, typically expect from any other modular proof system framework, if you're familiar with ArcWorks, for example, all the things available in their R1CS standard library are available as well. So things like fields, booleans, non-native integers, range checks, all the things you want. And then also cryptographic primitives that are written in ECLAIR itself, like written in the ECLAIR language, for things like accumulators, encryption schemes, signature schemes, anything you want. And all of these things are composable with each other by selecting the appropriate language features defined by the Rust traits. So here's a snippet from the duplex sponge encryption implementation. This is a way of taking a permutation and turning it into an encryption scheme. And so what you can see here is that the encrypt interface is a trait that gives other ECLAIR programs a standard interface for using encryption, and the duplexer is a structure that implements the interface. So we can see here highlighted in blue the references to the compiler that gives plugins access to constraint generation at these locations. So in any of these places where there's blue, a specific proof system can say, look, I know the best way to run this function in my proof system. Let me do that for you. And the user, the developer writing this gadget doesn't have to think about it. They just, okay, in Plonk, I know how to do this part the most efficient way. And I can just treat it as a black box. So this is sort of an example of this. And of course, Todd will also go into more detail in his talk. So now that I've spoken a bit about ECLAIR, let's sort of summarize some of the benefits of using using OpenZL and using this plugin system for your development stack. So first major benefit is that it solves this missing middleware problem for the programming stack. So there's lots of tools out there. Most of them are incompatible with each other, if not all of them. And with a simple plugin, any existing tool can be adapted to fit ECLAIR. So the amount of code you have to write to integrate your proof system or your language or your security tool into ECLAIR is on the order of hundreds of lines, not tens of thousands of lines. And you can now get access to this whole ecosystem. For proof systems like ArcWorks, an ECLAIR gadget is interpreted through the plugin as a constraint synthesizer. So if you're familiar with ArcWorks, this term will be familiar to you. But still, even using just ArcWorks, ECLAIR, it actually gets some more guarantees than ArcWorks gives you. So it gives you some type system level guarantees at compile time that your gadget computes the exact same witness that you expect to get if you just ran the gadget through Rust, for example. And you also get access to better type level guarantees about public inputs and private witnesses. For languages like zircon, a plugin would give OpenZL access to programs in that language by transpiling them into ECLAIR. So we can cross the bridge from high-level language all the way down to proof system. So this gives us the benefit of letting us migrate code bases between languages over time. We don't have to rewrite all our production code. Let's say you want to go from zircon to Halo 2. You don't have to rewrite all your zircon. You just go through ECLAIR in between. So these language plugins are future work that we'd like to start development on, but haven't started yet. And finally, another point for future work is the security tool suites. So if we run any of our gadgets through a compiler like over the tool called Picus, developed by Veritice, we can get out symbolic programs and static analysis reports about our gadgets so that we can run audits directly on the code without having to rewrite or hand analyze these programs, which for complex applications leads to fatal mismatches between specifications and code. This is like sort of the most common problem in verification, is that, oh, I didn't even verify the system I was trying to verify. And so in ECLAIR, we actually can use the Rust type system to guarantee it's the same program that you're checking. Another benefit of using OpenZL is that it gives you a unified deployment experience. So for application developers building like products, they can expect the same deployments no matter what proof systems they're using. And in newer versions of OpenZL, we're expecting things like CLI tools and integrations directly with existing pipelines. Like if you're using Polkadot for Polkadot, you get things like palette support, and if you're on Ethereum, things like hard hat support, these kind of things. And finally, one of the coolest and most powerful benefits, I think, this is sort of like, now I'm nerding out here, is mutual recursion. So this is something that's not really been possible yet. And it's because there are so many proof systems these days. And if you want to do recursion, you sort of have to write a recursion for every single combination that you want. So if you have 4 different proof systems, you'll need to write 16 different implementations. But this is like insane, and nobody's going to do this. But if you wrote it in ECLAIR, you actually only have to write 4, because any code that's written in ECLAIR can execute on any of these proof systems. So if you wanted to write a PLONK-2 verifier in Halo 2, you just use the PLONK-2 verifier in ECLAIR and compile it in Halo 2, or compile it in ArcWorks, or in Nova, or whatever. So this sort of hub and spoke model lets us leverage this cross proof system compatibility super easily. So we can start building mutual recursion right now instead of spending months and months doing each one by themselves. And because of the unified deployment pipelines, we can also get much better benchmarking tools across all of these. So it's way easier to just start writing benchmarks for all these things, because you only have to write 4 instead of 16. So this is another like super huge benefit of using something like ECLAIR. So where are we at today? So right now, we've currently built the ECLAIR standard library and the OpenZL crypto primitives library. And we have 2 plugins currently supported, so ArcWorks and PLONK-2. And we're looking at other plugins like Halo 2 Community Edition, CIRCOM, lots of other things in the pipeline. And OpenZL has already been used in production at Manta, and our Manta Pay circuits are built using ECLAIR and ArcWorks Grow 16. And we're currently actively running a trusted setup. So if you want to check out the status of that one, you can go to ceremony.manta.network. And also feel free to visit the OpenZL repo. And you can also go to our docs page at openzl.org. Yeah, so that's all I have. But thank you to the Polkadot Treasury for funding the development of OpenZL, and thanks to everyone for coming. I hope you enjoy the conference.
All right. Thank you very much, Brandon. I think in the interest of time, we'll take one question. And so we've got a question here from the audience. To clarify ECLAIR, is ECLAIR a programming language for defining constraints?
Yes. So ECLAIR is a programming language embedded in Rust. So it's a style of writing Rust code, and it comes with a bunch of standard library tooling inside of Rust for defining constraints. So this is the sort of thing where you could write something in CIRCOM or in ECLAIR. It's the sort of at the same level of writing constraints, but ECLAIR gives you direct access to proof systems. If you want to do some custom stuff, you sort of get access to that directly because you're built in Rust. So you get access to all the Rust ecosystem. You can use crates and packages, all that kind of stuff. But yes, it's a programming language inside of Rust.
Awesome. Thank you very much, Brandon, for that opening conversation around OpenZL, all the progress that's been made. And again, thank you to the Polkadot Treasury for funding the initial development of OpenZL as well. And so without further ado, we'll move on to our next session. I'll be ending this session